we talk about compounding and harmonics, we'll talk about how that differs with those. So you have all these sound waves coming in. You know, I mean, they get through the tissue, but every time they hit something, the transducer will pulse, let's say 3 sound waves, boom, boom, and then it'll stop, and then it'll listen for what comes back. And it'll do that a specified number of times, how the machine's set up, and that'll put together one frame. So it'll do that, let's say 5,000 times, which is probably 1/50th of a second. It'll do it 5,000 times, and then it'll listen to what comes back. So these same transducers, these same crystals right here, will pulse 3 times and stop for the amount of period which would take about, a pulse. Do that 5,000 times, and that creates a frame, and on a 4V1, it'll do that 25 times every second. That's where you get your frame rates. So if it does it 5,000 times, the information it gets back over those 5,000 times, it presents the information for the frame of what was most averaged when it came back. If there was some little random spike in there, one of those images throws it out. So it is incredible what those ultrasound systems do that we all take for granted, and that's why I know from your standpoint, the machine has to be put together so that there's no outside interference and noise, because if the machine, is going to clutter up the image with, excess noise coming from inside the electronics, it's just an electrical current that comes down that cord, plain and simple, that excites these transducers. I mean, it's most basic, and that's how you put together your image. So that's what it does. And when it comes into the tissue, kidneys kind of actually have 2 different types of tissue in here. Depending on the type of tissue will depend on how much of the information does not come back, depends on how fast the information gets back to the transducer. Ultrasound machines are set up so that in the average body, sound travels 1,540 meters per second. Well, you're not sending stuff meters, you're sending stuff, 15 centimeters. Not, it goes 1,540, actually add 2 zeros to that, so 154,000 centimeters per second. Sound goes there, and then it takes that amount of time to come back. So it's doing all of that at that very near image, and depending on how long it takes the information to come back, the machine decides what type of tissue it is. For instance, I said 1540 for soft tissue. Fat, when you're going through a body, we all got the fat going. Sound travels slower through fat. When you hit muscle, it's denser, it travels faster. When you hit bone, it travels, about twice as fast through bone as it does through soft tissue. So sound can travel at different speeds depending on the medium that it's going through. In the air, sound travels about 300 meters per second. Water, closer to what the body's made of, right, is 1480. And then, a railroad, piece of steel on a railroad track. If you hit that with a hammer, that information, that echo through there is going to travel at about 7,000 meters per second. So the denser the fluid, the closer the molecules are together, the closer that information is, transferred from one molecule to another. Air, is much slower. In a vacuum, if there's no molecules, there's no sound transferred. So, in space, if you were in a vacuum and you yelled at somebody, there's no way for that information to get from your mouth to their ear. They wouldn't hear a thing. It's kind of hard to believe that way. I think I could prove that wrong. They'd have to hear it. So it's just, sound is energy. Windows, double pane windows or vacuum in between. The whole theory is the outside of the window can heat up, but if there's no molecules to excite in between those 2 pieces of glass, that heat cannot transfer from one side to another. So that's, heat is energy, sound is energy. all of our imaging transducers are pulse wave, meaning that crystal that we talked about, it sends information and then it stops sending, and then the sound that comes back, that vibration that comes back, goes back up through the cord, stores it. That's how it puts together the frames per image, and then frame rate per second. So that's a pulse wave transducer. Continuous wave transducer, they have two crystals. One is always sending, and one is always listening. So you have two crystals in a continuous wave transducer. These are not 2D transducers. They're non-imaging probes. And the benefit of these is there's no aliasing, and that's another question that was sent out there. And it applies to Doppler, to blood flow, which we'll get into also. But continuous wave transducer, non-imaging, it's always sending, it's always receiving, and I'll get into why that's a benefit over the aliasing when we talk about color Doppler, because that's where it plays in there, the Doppler effect. And again, why would you choose one over the other? Continuous wave transducers are going to be used for blood flow most of the time in the brain. When kind of the physics, when I was going through college, I made my money doing landscaping. I always thought that's what I'd do when I retired. And so, you start off with the biggest pipe at your water source, and when you get out to your sprinkler head, you're maybe the 1/2 inch, but you start your house at 1 inch. So if you're sending, 5 gallons a minute through this big pipe, and all of a sudden you want to push 5 gallons per minute through the small pipe, the speed at which that blood goes through that pipe is going to increase. There's mathematical equations to tell you that. Well, when you're looking at blood flow, let's say in the brain, and all of a sudden you get a stenosis, where that vessel, that artery clamps down, blood's still going through there. They want to find out how fast it's flowing. You come in with your transducer. This will be the skin level. You come in with your transducer, and we'll just kind of get to this. Who's got a ticket by a police officer with radar? Okay. No kidding. So do you know how it works when they do that? It's kind of, it goes back to, if you were at a NASCAR race or you're watching it on TV, the car's coming up, and then when it's going away, well, it didn't shift gears every time when it passes you. That sound wave is coming out of the car like this, and because the car is coming towards you, it increases the amplitude, increases the frequency of it. It sounds higher pitched. This is what an ultrasound machine does when it's looking at blood flow. The most common place we look at blood flow is in the carotid artery. So when you're coming down the road, Johnny Law's sitting out there, if this is the road coming this way, they don't sit like this. When you come by, they hit you. Because if they come by, if you drive by and he bounces off your car right there and comes back, your car didn't change any distance between here and there, right here. It did a little bit, but the equation doesn't work. They got to set up at an angle. They got to have you coming towards them or going away. And the angle has to be less than 60 degrees. There was actually a guy, Dr. Doppler, sounds funny, but that was his name. And he's the one that invented this equation. It's got to be under 60 degrees, that's 90 degrees. So it's got to be under 60 degrees. And there's an equation for, I send a frequency out to you. I know it takes a second to get there. And if it gets back in 0.98 seconds, that means you're coming at me. It hits you and it's coming back faster. If it takes longer than a second to get back to me, that means that it hit you, but it hit you twice, and the second one took a little longer to come back. That means you're moving away. So that's exactly what we do in ultrasound when we're looking at carotid arteries. And we're using the continuous wave probe in the brain, these little tiny vessels. The velocity can get so big if you were using like a 4v1 transducer. this velocity, just to use round numbers, if we were coming in at 100 meters per second right here, the velocity here could get 400 meters per second. When the transducer is, as we discussed here, it sends out and then it listens. If the velocity is coming so quick, it sends out, and before it stops to listen, it comes back already. That's where you get aliasing. That's where you get the information coming out of the transducer and coming back collide, and then you get garbage. So, a lot of times you'll see, red and blue are the two colors we like to use for our color Doppler. You'll get orange and yellow and all of this. That's aliasing, meaning we don't know which direction it's going. The information just got cluttered. The definition of a sector image was back in the day when transducers were mechanical. And again, not everybody has been around ultrasound as long as I have, singing about as rickety as it can. A friend of mine was in the military. He used to have to give presentations to people way up, the generals and stuff. And you had to race up back and forth like this. You couldn't go like this because your butt shook. They think about that stuff. It was disrespectful to the see, up and down, never side to side. They had a way to do everything with the felt pin. But a sector image is from the day, and this will look familiar, where the image looked like this. When transducers originally became real-time, there was one crystal in the head of the transducer, and it just went back and forth like this. A wobbler had fluid all around there, and if you're talking to somebody and they mention a wobbler, they've been around a long time, and that's how it would make its image. And that gave you a sector-looking image because you just had this one transducer here and it was going back and forth like this. With phased array transducers, the face, again, of that 4V1 transducer is going to be like this, 96 crystals. They look similar, but here's the key right up here. The sector comes to a point. This is just going to be, it's called a trapezoid. And so phased array transducers, if you had to use the right term, it's a vector. Keep losing my little piece of paper. Any questions so far?
On the transducer, I assume the crystals are at a slight angle as they, or am I all the way on it?
Good. A slight angle, exactly. And then you can also do beam steering out of these angles, or out of each crystal. A good example is GE's 9-linear transducer. Okay, so here's your transducer. It's got all these crystals. Normally for a linear transducer, that's what our image looks like, right? On the Sequoia, we can plug in the 6L3. That's the image you have. Beam steering is what you'll hear that today. This is what the image can look like. And then the new Sequoia 9L5 maybe, that transducer can create a trapezoid. And what it is those crystals, they can actually shoot out up to, I think it's a 7 degrees off axis and create that trapezoid image. So within that, they've got the ability to beam steer. And it's done with some heavy electronics as far as lobe artifacts and all of that. You get it, the more you learn about it, you get more of an appreciation for the people that designed this equipment. They're into sending out an enormous amount of information, getting back as much as they can, and then sifting out what they don't need. On your average ultrasound signal, 100% of the sound goes out, 2% is received back, and you put your information together off of that. The rest of it is absorbed The rest of it hits something and, goes off at an angle, never to come back to the transducer head. The transducer doesn't see, it just listens and puts together information on what it hears. So only 2% of it comes back. That's why when you do your transducer testing, you have the two different components of it, how they're firing out and how they're receiving back. You gotta have both. Okay, so let's say you're looking at a breast image here. And right down here in the breast, you've got something bad right here. Don't know what it is, but you're going to take pictures of it. Traditional ultrasound, it just shoots our little information down. Okay, out of all the crystals, hits it and comes back. So in reality, your ultrasound, for the most part, is just hitting the top half of this. You can see the bottom for the throughput, but it's just hitting the top half. What compounding does, and it's about the beam steering, is it takes that same transducer, same little nugget, and it hits it straight on, and then it beam shifts so that it has beams coming at this angle, and at this angle. So now all of a sudden you're kind of kicking around the edges here and getting a little more information. When we're looking at a nodule in the thyroid and a breast imaging, calcifications are very telltale as to what it's made up of. So when you see calcifications, you see the shadowing below it, you lose information. That means it hit something, let's just call it like bone. That information was lost, but that tells us something. Compounding, you lose those little markers coming down, but you do gain information, coming around the structure. So you get more of a definition, defining of what the nodule looks like. That's beam steering compounding, which is done most of the time. Some systems also have frequency compounding, where they'll hit the same area of interest at different frequencies, getting back different information, and then putting that together for a more detailed image. So compounding gives you more detail. Ultrasound is all about trade-offs. With more detail, it takes longer to do it, you get slower frame rates. So compounding is great for things that don't move. Thyroid, breast, testicles, shoulders for musculoskeletal. Those things, the respiratory system doesn't really move that much. When you start using compounding on the liver, trying to pick up liver mets and that type of stuff, the person's going to be breathing. Your frame rates are going to be such that, at 8 frames per second, you get a blur because it's moving the whole time. Whereas at 8 frames per second on a thyroid, it's going to be beautiful. So compounding is primarily, it was developed initially on the linear high frequency transducers because, again, they're things that aren't moving, but now all of the transducers have it. So, if you see a lesion in the liver, have the person take a big breath in and hold it, stop that movement, you can get a better image with compounding, but you are going to have slower frame rates. So it's just a trade-off there.
Question I have here. On compound imaging, the outside element being in there, how important it is or it is not? All the elements are in the corners are they're not dead or.
If you had to, you could operate and get by on a system, that these elements were toast. You'd lose the ability to, interrogate out here. But they all do play into it. That these elements on the outside, for the most part, fill the image on the lateral parts. They do.
What about on the compound imaging?
On the compounding, it's up to about 7 degrees, I think. If they didn't play into hitting the structure. If you knew what you were looking at, that's one thing. If you're surveying, you don't know what you're going to find, then these outside borders, you could come across the information that you're trying to look for. So, Conquest is one of the most specific, really nitpicky on transducers, and that's great. I mean, it's, you know, you can get away with one element being bad in here because it'll be covered up 10 times over by all the surrounding elements. You know, you're not going to lose something like that. Ultrasound, for the most part, is good to find things to about 2 millimeters. That's what they'll say. You know, we know what a centimeter is, so 1/5 of the centimeter. That's pretty much what ultrasound sets as standard for. You should be able to find everything up to that. Your phantoms, I think they'll go down a little smaller than that. That's fine. You can see smaller detail with compounding. Start hitting that one point, different directions, all of a sudden that little thing comes out. So, you know, when you, next time you're testing a transducer, 15 LAW on a phantom, you know, run it at 14, you know, megahertz, see what it looks like, and then turn it down to, you know, I think you have compounding at 14, HC14. Boom, you'll pull in the smaller information. For people selling transducers, that's why that transducer or the machine that'll do compounding is worth more. Because, you know, I mean, it's more information. Frequencies, higher resolution, more detail to an image. Think of higher frequencies as megapixels in cameras. In the last 10 years, we've seen, you know, a 2 megapixel Pentax camera, great, and now what are the iPhones, 10 megapixels? You know, they're incredible. Think of high frequency as high megapixels. That higher frequency comes in contact with more information. So by changing the frequencies, you change your image absolutely. If I'm, you know, on a real sturdy guy looking at his liver and trying to find some, you know, metastasized cancer in there, I would love to be able to image that liver at 8 to 10 megahertz. But the physics of it will not allow sound to get that far and to come back to any degree that we can listen to it. So I'm forced to go down in frequencies. So what the sonographer should always do is try to use the highest frequency to get the image. So frequency, you'd love to operate everything at 15 megahertz. And there's an equation for, you know, the energy that's lost for every centimeter depending on the frequency. You know, those are what the physics guys are all about. So, you know, as you're talking to customers, you know, what are you going to use your machine for? Vascular access. You know, going to be looking at veins. We're going to be, you know, killing veins. Great. Veins near to the surface, higher frequency. You're going to start talking about image resolution and higher frequencies. And so telling the doctor maybe that, you know, has a 6 megahertz linear, which was one of the first linears that came out, and they're seeing the veins. When you start talking to them about a 10 or a 12 megahertz, you can honestly tell them they're going to see the backside of that lumen. You know, when they're working with veins, most often it's not so difficult to find a way to it that you can't find if you went through it. So to be able to show that backside of the vein, for instance, that's conversations that you'll have with your customers that, I mean, that means something to them when you're talking to the lingo. I think we're talking about this notch here and this notch over here. When we use a needle guide, kind of the rule of thumb is whenever you have a biopsy done, the doctor's using a needle guide, run. Because they're the ones that's training wheels for radiologists. The needle guides set up right here. They've got a little notch, if you haven't seen them, where the biopsy needle can go in. You have a needle guide option on the machine that shows a little dotted line on where the path of the needle will go. That's what it's for. The doctors that you want doing your biopsy, they look at the machine, needle, and it's just in their head, it's all one and the same. They see the needle with the ultrasound transducer, they find where they want to take the biopsy, they take it. But that's what the notch is for. And then what's the big notch on the side for?
Direction.
South bottom.
Okay, so it's a reference point. It's very specific. So if I've got this notch pointing up and the machine's just set up kind of normal. What's that gonna mean? So I'm looking like this, what's that gonna mean on my image? Because remember, the image on an ultrasound machine, you know, I'm scanning like this, but what you're actually seeing on the machine is this. The ultrasound image, think of it as a fan. It is just a thin 1 millimeter sheet of information that when you put it down in the body, it just shows you that little point in time, you know, for that little space when you move around like that. So when I've got this long notch that the sonographer can feel, you know, in a dark room, I'm doing this, or doing this. What's on the left side of the screen? Or I'm sorry, yeah, the left side when I'm looking at it.
It's the marker corresponding to that spot.
Right, it's gonna be superior and inferior, top, bottom. When I hold it in the body, the sonographer will always try to have the notch pointing up or the notch pointing towards them if you're doing general imaging. Because when the notch is towards you, the information on the screen that is on the right side of my body will appear right here. So that's for the radiologist. You know, and that kind of one of the other questions that we'll come across is, you know, you can invert the image. You know, so the little Accusson A is not on this side, it's on the other side.